Hello and welcome to the first video that I'm making for the level 1 targeting maths course. Let's crack right onto it with what's this? 1.12 demonstrate understanding of charts and data. There's some information up the top here which is for the most part not really important. Well, it could be important as it's worth 4 credits and it's an external, which means it's an exam at the end of the year. During these videos I'll be switching between me and my face so we can talk face to face. Although it's not really talking face to face, it's more me talking at you, but at least you get to see my face. And the workbook here. If we scroll down through the workbook, we've got the contents page. Cool, pretty self-explanatory. The sample question about basketball, we'll go through that during class. So if you're not in class, like you're sick or you're catching up or you're getting ahead, then just wait for class. After the sample question, there is the homework tracking. Again, in class I'll explain more about what I intend for each of these columns, but even if you're not in class, they should be self-explanatory. I'll switch between myself and the workbook depending on if I want to point things out in the workbook or if I want to have a bit of an explanation time about a concept or about a particular idea that it talks about. But let's crack on with Lesson 0. What's the title of it? Lesson 0. Our inability to intuitively understand probability. What does that mean? It means that we don't intuitively understand probability. And what does it mean to intuitively understand something? It's like if someone asked you 2 plus 2 equals 4, but why? Why is 2 plus 2 equal to 4? And it just makes sense. Like, I'm trying to think of an explanation, a way of describing why 2 plus 2 equals 4, and it just is. It just makes sense. There are other things that make intuitive sense to us as humans. Probability is not one of those. Probability is something that we think we understand fairly well, but we really don't, which is a shame because it would be better if we knew we didn't understand it. If we're like, I don't understand probability, I need to stop and think about this. But we think we know what we're doing and we end up coming to the wrong conclusion from our intuition. And you might be sitting there thinking, David, I have a fairly good understanding of probability, thank you very much. And maybe you do. I mean, and who am I to say that you don't? But I'll give you some examples to show why probability just doesn't make sense at first glance. The birthday problem. The birthday problem asks, how many people do you need for it to be likely that there's a birthday in common between 2 people? We're not interested in the year, only the date. And that if you have 2 people in a room together, the chance that they share a birthday is very small, very close to 0. But if you add more and more people, then there's a higher and higher chance that 2 people share a birthday. And at what point is it more likely than not that 2 people share a birthday? In other words, when is there a greater than 50% chance? Is it half of 365, 180 something, 182, 183? Is it 200, is it 100? We'll answer this with experimental probability. Let's go through all of the students and, well, hang on, experimental probability, what does that mean? Experimental probability is when you do an experiment to try and work out what the probability is. That's compared to theoretical probability where you do calculations, you get a calculator, do pen and paper, and you try and calculate the probability. The calculation is a little bit tricky for this one, so we'll do it as an experiment to get a ballpark figure for how many people you need. It's not going to be the exact number, but it gives us a ballpark. So let's use experimental probability. Let's go through all the students in this class and ask what day of the year they're born on. Then move on to students in other classes until we get a birthday in common. And how many people did it take? Write it in the table below. Just there. We can do a similar simulation by generating random numbers. Generate random numbers from 1 to 365, 1 for each day of the year, until you get a double up. How many did it take this time? Do it multiple times with some friends until you have 5 results. So we should be getting roughly the same number, like if the number is 200, then we might get like 180, we might get 220, we might get 250, we might get 160. we might get 205, but we're always around the same number-ish. It gives us a ballpark figure. After those 6 experiments, feel free to watch this video. Actually, do watch this video, because it explains more of the theoretical probability. And in class, we'll do a little bit extra where we visualize the theoretical calculation. And in class also, we'll ask a similar question. How many people do you need for it to be likely that someone shares a birthday with you? It sounds like a very similar question, and it is a very similar question, but it's slightly different, and that slight difference makes all the difference. And in class, we may talk about why, but they are two very different questions. Another way that our intuition leads us astray in probability is the Monty Hall problem. This is a famous problem in probability theory. It states you're in a game show, and in fact, just by the way, this was a real game show. So back in the day, not sure how back in the day it was, but this was an actual game show on TV, and you could play this for money. You could get a car on this show. So, fun fact. Anyway, you're in a game show. There are 3 doors, and behind the doors are 2 goats and a car. So behind one door is the goat, behind one door is a goat, and behind another door is a car, but you're not sure which one's which. You pick whichever door you want. The host, who is called Monty Hall, opens one of the doors and reveals what's behind it. He can never open a door you've picked, and he would never reveal the car, because then the car's revealed. He then offers you the opportunity to switch to the last remaining door. A little bit tricky. Okay, so there's 3 doors. 1, 2, 3. And behind those 3 doors, there's 1 goat and 2, 1 car and 2 goats. You pick one door. For example, you pick door 2. Monty reveals a goat behind door 1 and offers you the opportunity to switch to door 3. So he'll never reveal a car, and he'll never reveal what's behind the door you chose, because that makes your choice, very easy. What should you do? Should you switch or should you stay? Or does it not matter because it's a 50-50 chance? Again, we'll use experimental probability rather than theoretical probability, although we could do theoretical if we want. Simulate this with a friend, one of you being the contestant and the other being Monty Hall. Do it 10 times switching and 10 times staying. You can choose in what order you do them. You could do like 10 times all in a row staying and 10 times all in a row switching, or you could do one of each. However you want to do it. But overall, do 10 times when you switched and 10 times when you stayed with your original choice. And record the result. Did you win the car or did you lose? Did you get a goat? And the person being Monty Hall needs to remember the rules for which door to reveal. Please don't reveal the car, and please don't reveal the door that the contestant picked, because that's not the game. You can also use theoretical probability to explore this situation, and this is explained in the following video, which I do recommend you watch, and we will watch in class. And here's a little bit of an extension to finish the class off. The dotted border tells you that it's extension, and you don't need to know it, but it's good to know. It helps flesh out the ideas that we're exploring here. Why did the ancients locate their monuments to form exact triangles? How did they do that to such precision? Why do songs have lyrics that work both backwards as well as forwards? And how does wingdings predict events? Matt Parker explains. This is a lecture by Matt Parker. Fair warning, it's 63 minutes long, but it's really helpful in fleshing out these ideas of why we don't intuitively understand probability, and it is a fascinating watch. It is a lecture though, so it's a good illustration. It's a good idea of what will happen in university. You sit down in a seat, and for an hour a lecturer stands up there and talks, and you either write notes or you listen and check the lecture slides at the end. Maybe they'll give you a transcript of what they said, but that's how you learn in university, so feel free to have a look at it. That's the end of this class. Next class we're looking at lesson 1 something. Lesson 1, theoretical and experimental probability, and we'll talk more about the difference between each one. But until then, see ya.